No introduction necessarily, let's just get straight to it. Okay, the very first thing that we want to look at is solar cells. Okay, so the key thing here is sunlight can be used to make electricity. Okay, light making electricity, and these are solar panels, which is what we use to be able to make them in the first place. Why is this better than using coal power stations? Well, they make DC. Well, why is it better than coal? Because it doesn't produce any CO2 gas, which is responsible for global warming. They also make DC electricity. That stands for direct current. You imagine light falling on these panels, and they will make electricity just going in one direction, which is why it's direct current. So always remember that, don't forget it. But power stations, they make AC. Okay, that's alternating current, which has got to do with the magnets, but we're going to talk about that in a second. Advantages of solar cells. Okay, number one, they're low maintenance. So once you've set up a solar cell, it's not really any moving parts, so very rarely can things go wrong with solar cells. There are no power cables apart from the cable that connects that solar panel to the device that you are using. When I say no power cables, I was thinking more on lines of no connection to the national grid or anything else like that, and they can be reused in remote, out-of-the-way places. Imagine that you've got a bungalow. I don't know why a bungalow, but you've got a bungalow somewhere in the middle of nowhere, and there's no easy way to get electricity. Get solar panels, no problem, easy peasy. And they're also renewable, which means that they won't run out. Coal is non-renewable because one day it will run out, and it's finite. Remember that from C1. And there's, like I said, there's no pollution like CO2, which causes global warming, and there's no sulfur dioxide, which makes, yes, you're right, it makes acid rain. Okay, but there are disadvantages, unfortunately, and those disadvantages is that you need sunlight, which is obvious, as it only works in sunny countries and they don't work at night. You can get solar panels that work here in the UK, but obviously it's not going to work as well somewhere like in the middle of a really, really hot country like Spain or something. Passive solar heating. Now, passive solar heating isn't about using light to make electricity. This is all about using heat from the sun to heat things up. So, for example, you can get windows in a south-facing home. Okay, so say, for example, some part of your home will be pointing south where the sun is going to be shining the most, as in when you get the sunrise. If you're facing the south, because that's where the sun will be, you can absorb light energy, it'll heat from the sun during the day and let it out at night. So this would be a south-facing house. And you can see that this is passive solar heating, and that the sun will be shining into your home and heating up the walls, and heating the house up, which is why it's always a good idea to have big windows in a south-facing home, and that will heat it up, and it will heat your house up for free. How's that? No problem. Or you can use a solar cooker. Now, a solar cooker is like a dish that is shaped like that, and when the sun's rays hit this panel, they will reflect back out to the food and heat up the food, or water, depending on what you want to do. So it could be a solar cooker as well. Okay, now it uses the sun's heat to heat up the food, I told you that, and the mirror is curved, and so it focuses the light on the food being cooked, and it cooks it up from infrared. So if I just draw what it would actually look like, okay, so yes, I know, I don't know why I always pick red, and so this would be the solar cooker, and if you had heat coming from the sun, okay, the sun's heat would be going this way, and it would be going this way. And imagine that the food is here, yeah? The light rays would bounce and hit the food right there. And that's how it would be. So if they show you a solar cooker, you just basically, you've got to use the light rays. And it would come in from any direction, really. Like if it would hit here, it would bounce up there. And it focuses the light over towards, it focuses the infrared radiation right here. Okay? So, did you know wind power comes from the sun? Oh, no, you didn't? Well, it does that because these are the wind turbines right there. It does that, and some more wind turbines, and it does that because some parts of the Earth are going to be heated up more than the others, and so if it heats up more around the equator, the air gets hot and it rises. Remember P1, and then the colder air would then take its place, and that's convection currents, yeah, and that is what wind is. And so, like I said, this is a convection current, and it turns kinetic energy, as in kinetic means movement, from the wind, and it turns the blades of the wind turbine right here. So the wind will be coming in, turning these blinds over here, and all there you have a magnet inside a coil of wire, and that makes electricity. Yeah. So you need to know the advantages of wind power as well. So first advantage of wind power is that there's no pollution, no CO2, no sulfur dioxide. Very good. It is renewable. It will never run out. And the disadvantages is that sometimes it's not windy, and so it's not reliable. Sometimes the wind's not strong enough. So that is a disadvantage. Space is limited in windy, really, really windy places, and it spoils the view. Remember me telling you about my friend of mine who's got this house in the countryside, and they wanted to put up wind turbines, and he was very angry about it because he bought this beautiful cottage in picturesque Wales, and they wanted to put up wind turbines, and they didn't, so he won. Power stations. Okay, now power stations. Most of the electricity we use comes from power stations, and so the electricity goes to everyone through the national grid, and the power stations are all connected through a series of power lines, okay, like these. And this is all the power stations connected to all these pylons make the national grid, and your home will be connected to these through these cables, etc. Okay, now we need to know how power stations work. So this is how they do. First of all, you burn coal, yeah, and that produces the heat. The heat then heats up water, okay, and turns it into steam. The steam pressure builds up and turns a turbine, and the turbine turns, which turns a generator, okay? So the generator then makes electricity, okay? And then it goes into the pylons and then into the national grid. Now, the generator is literally just a magnet, okay, with a causal wire going around it, and as it spins, that makes electricity. And it pretty much, the key things to remember is that the turbine turns and the generator generates electricity. Now, this is a little animation looking at how this works. I'm just going to skip this, but basically it works like this. So the boiler is going to heat up the water, okay, the water's right there, and the water eventually is going to turn into steam. The steam is then going to turn the turbine, and the turbine is then going to spin the generator. Now, inside there, like I've already told you, is magnets and coils of wire, which is how you make electricity, and then that goes into the national grid. Now, often when you see power stations, you will see these big, massive cooling towers. People think that's where the electricity is made. It's not, because all that steam goes into these cooling towers, hits to cold concrete, that turns back into water, and that will go back into the boiler. Otherwise, you'd have to use constant supply of water, more and more water, and we'd run out of water in that particular area, and so we need to ship in water, which costs even more money, and we don't want to do that. Okay, so just going back here, is that coal is typically used to make the heat, isn't it? Okay, but we can use anything to produce that heat, to turn the water into steam. So for example, nuclear power stations can produce heat, and that turns the water into steam, and then the rest of it is exactly the same. But we can also use something called biomass. Now, biomass, just like the word, what the bit of the word bio, okay, now bio just means biological, so it could be trees, it could be straw, it could be manure, it could be gas, okay, and that is any mass that comes from something living, okay, not gas, unless the gas was produced from living things, like decomposing organic matter. Don't worry about that, but let's just get on with it. Anyway, so we can use anything to heat up the water. So we can use nuclear power, we can use biomass like wood, straw, anything like that. Okay, so that's how a power station works. So you need to know the order of which. If I were you, I would pause this video right now and see if you can come up with the order. Pause it now and list the order that it should go into. Pause it. Come on, pause it. You're not pausing. Pause. Okay, now this is the order, so see if you got it right. There you go, that is the order in which it goes. So if you didn't know that, rewind it again, and that is the order of how a power station works, and you've got to know that, guys. You've got to know it. Okay, so moving on. Calculating efficiency. Now, we've done this in P1, okay, and efficiency okay, like I've already told you, is about useful energy divided by the total energy going in. Now, you have to do that. So, for example, if I had a light bulb and I supplied 100 joules of energy to it and it was converted 20 to light, yeah, 20 joules is the useful energy, and the total that it received was 100. And so you do the simple calculation of 20, I know, terrible writing, divided by 100, okay, and because it's an efficiency, you've got to multiply it by 100 as well, because it's a percentage, and it will give you what the answer should be, okay. So, for example, if it was coal for a power stations, that contains 10,000 MJ. Now, they might use MJ. Now, MJ just stands for, that's not Michael Jackson, it stands for megajoules, which is a million joules. So 10,000 million joules of chemical energy in coal. If the power station produced 3,800 megajoules of electricity from this coal, how efficient is it? Well, it's not very efficient. So you should already be thinking, well, hang on a second, 3,800 is the useful energy, because that's electricity. 10,000 joules is the total energy going in, so the calculation should be 3,800 divided by 10,000, which would give you 0.38, which again, you multiply it by 100 to get it into percentage, which would be 38%. Okay, so that is efficiency of power stations. Okay, as long as both of them are in the same units, the MJ and the MJ, then all is good and well in the world. Okay, so generator makes electricity by spinning a magnet inside a coil of wire. Making electricity really is that simple. So you can make electricity at home right now. Just get some magnet and some coil of wire connected to like a little bulb and spin the magnet, and that will make electricity. Okay, now that is called the dynamo effect. Okay, now you notice here we have got a coil of wire, we have a magnet. Move the magnet in, you see the current would go that way. Now, we move the magnet back out, okay, the current would go in the other direction. Can you see that? Yeah, so if we went in one way, yeah, it would make electricity. So go in one way, positive, move it the other way, negative. One way, positive, other way, negative. That's why, can you see how that current is alternating? Yeah, because that's how alternating current is made in power stations. That is why alternating current is made in power stations. So the electricity is alternating. Yeah, so making electricity really is that simple. One way, other way, one way, other way. Okay, easy peasy. Yeah, that was weird. If you don't move the magnet, you're not going to get any electricity produced. It really is that simple. So, three things. By the way, that I don't think I stressed this enough. When the magnet's going inside the coil of wire, that is called electromagnetic induction. That is production of electricity in the first place. So, there are three things that affect how much electricity can be made. One of those is the speed of the magnet. Put the magnet in faster, more electricity. Strength of the magnet. The stronger the magnet, the more electricity you're going to be producing. And the number of coils of wire also has an effect. So if you put loads and loads and loads of coils in here, you're going to get more electricity produced. In actual fact, if you have a look at the power stations, the coils of wire that they have, there are thousands and thousands and thousands of coils inside these really strong magnets, and they move it around really fast. They move it around, I think it's 240 times every single second, yeah, which is why your plugs say 240 hertz, because it means it's spinning round 240 times every single minute. Now, DC is not the one that is produced in power stations. AC is produced in power stations, but DC is direct current, which means that current is only going in one way, and these batteries are always direct current, okay, and solar panels are as well. Yeah, we got that? Excellent. So, greenhouse effect, I've already talked about this. These are the three things that contribute to it. Methane, water vapor, and carbon dioxide. Methane gas is produced when animals fart. I want to say that. Water vapor in the atmosphere, and carbon dioxide that we already know. So, I've been through this already, guys, in the B2. This is the natural greenhouse effect. So, sun shines down, some of it reflects back into space, some of it bounces back. If we didn't have these beautiful greenhouse gases, our planet would be too cold. But we are producing too many of these gases. So we're burning too many fossil fuels, so too much CO2. Also, we've got too much livestock, cows, which are producing too much methane, and too many rice fields. They also produce methane. And you've also got the nitrogen dioxides, which also contribute to the greenhouse effect. So we are making an enhanced greenhouse effect. Yeah, greenhouse effect is good. Too much greenhouse effect is bad. Okay, so these are all the things that contribute to it. So methane, and that is how they're produced. I'm not going to run through all of this. So just pause this video and watch it, and you can and read it, and you can see that these are the three main gases that actually produce all the bad things. So concentration of CO2, how has that actually changed? CO2 concentration, you can see from the 1700s, it was very, very low. 1800s, which is about when the Industrial Revolution started taking place, and the amount of CO2 is really, really started to increase, and you can see that it's going up. Now, is there a correlation, which means a link between that, the CO2 concentration, and the global average global temperature? You can see that as the CO2 concentration starts to increase, so does the temperature. Yeah, some people still aren't very, very convinced about this. And I have no idea why they're not convinced. Most climate scientists, or any kind of scientists, agree that this is taking place, but some people still don't. I find it pretty shocking, really. But anyway, no, less said about that, the better. So yeah, so you may get a data question in section D, and you may have to link up the concentration of CO2. So what you do is you discuss that, and you would use numbers from the graph. I've always said use numbers from the graph and match it up to the years and the CO2, and talk about how it's increasing. Okay. Now, fuels for power stations. Common fuels in power stations are fossil fuels. So you can use coal, you can use oil, you can use natural gas, and you can also use nuclear fuels like uranium and sometimes plutonium. Yeah, or renewable biomass like wood, straw, and manure. Yeah, so those are all the fuels that you can use for power stations. You have to know what they are. Okay, so fossil fuels, I've already talked about this, guys, that they are non-renewable, which means that once they're used up, they're not around anymore, and so they're finite. They contribute to the greenhouse effect and carbon dioxide, and they also, when you have the coal, it releases, I don't know why that says coal and oil. It's really, really only coal that produces sulfur dioxide gas, which causes problems for acid rain. Now, pause this, have a very, very quick read, but it's not something that I've already talked about. Okay, nuclear fuels. Now, surprisingly, nuclear fuels are also classed as non-renewable, which means that once we run out of nuclear fuel, there's no more left and it can't be made again. Now, large amounts of radioactive material are released into the environment, and that nuclear waste can be dangerous, and it can stay radioactive for a very, very long time, which means it must be stored safely. But unlike fossil fuels, they don't produce any carbon dioxide and sulfur dioxide, which is why some countries have started to move to nuclear fuel just to lower their carbon footprint. Carbon footprint means how much carbon they're actually producing, how much carbon dioxide. And all the countries are trying to lower that as per the Kyoto Agreement. Renewable, that wood, straw, manure are cheap and they're sustainable, and so the problem is that we don't have enough biomass to replace the amount of fossil fuels, etc., that we are using. So that was that. Calculating power. Now, calculating power, first of all, it may give you, there might be a question asking you, and it might ask you to calculate the amount of power something produces. And as you remember, that power is calculated in watts. Okay, so to calculate the power of something, we easily do the voltage multiplied by the current. It could not be easier, and it would give you the power in amps. Now, as an easy thing, it might say that a radio, I don't know why a radio, runs at 3 volts, and it has 4 amps running through it. Okay, calculate the power, and it will be the voltage, which is that, okay, 3, and the current, which is in amps, is 4, and that gives you how much power does it have, and it would be 12 watts. Okay. Now, what you have to do is you might have to calculate the amount of electricity actually being produced, the cost of electricity, sorry. And cost of electricity, when the electricity companies sell you electricity, they sell it you in units, and those units are called kilowatt hours, which is right here. See, kilowatt hours. That's the horrible. That was supposed to be a nice circle. It's not a nice circle. kilowatt hours, and that is produced, and you can calculate the amount of kilowatt hours by getting the power in kilowatts multiplying by the time in hours. Yes, you do remember this. And what you do to calculate the total cost of something, you multiply it by the total number of units, which is number of kilowatt hours, okay, and you multiply it by cost per unit. Now, electricity companies will put you on a tariff, and that is how many, the cost of actual electricity that you are going to be paying. So the electricity might be charging you 14p per unit, okay? And all you do is calculate the number of kilowatt hours that you used, i.e. number of units, multiply them by how much it costs per unit, which might be 14p. So this is a table we did in class a long time ago. So this one's easy. An iron runs at a power of 2 kilowatts and it's on for half an hour. How many kilowatts? Well, it's 2 times 0.5, so it's going to be 1 kilowatt. Cost per unit, I've said, is 14p. So the answer to this is 14p. Guys, pause this and have a go at this before, yeah, and see if you're doing it exactly the same way I'm doing it. This one's easy. An oven is running at 3 kilowatts because that's the power rating of the oven, and it's on for an hour. How many units? Well, kilowatt hours is 3, isn't it? Yeah, so it's 3 times 1, which is 3. 14p per unit. Now you really are testing me. So 14 times 3 is going to be 42. So this one is going to cost you 42p to run in total. Okay, a bulb, 0.04 kilowatts, which is basically 40 watts. So, and multiplied by 5 hours gives you 0.2. Yes, I did use a calculator for that. Gives you 0.2. So that is 0.2 kilowatts. Cost per unit is 14p. So you do 0.2. So 0.2 multiplied by 14. I already know this is going to be 2.8p. Yeah. So the bulb for 5 hours costs 2.8p. So bulbs aren't very expensive to run, and even cheaper when you've got the energy-saving light bulbs. Okay, this one is slightly trickier. This one, it gives you the power in watts. Now, you know that what we're interested in is kilowatt hours. So what you actually do is you convert the watts into kilowatts, and you do that by dividing it by 1,000. Okay, 1,000. Which was an easier way to write on this. I wish this was touchscreen. That made my life so much easier. Okay, so 2,000 watts divided by 1,000 gives you, I'm just going to put another line in here, and that is going to make 2 kilowatts. Okay, now it's on for 10 minutes. We're working in hours. How do you convert minutes into hours? Well, that is really, really dead easy. All you do is you divide the 10 minutes by 60, because there's 60 minutes in an hour, in case you didn't know that. Of course you did. And that gives you 0.16. Okay, well, there's actually two decimal places, so it's actually going to be 0.167. That's what that's supposed to look like. Okay, and so you do 2 times 0.167. That is, oh, no, this isn't working. Hang on 1 second. 0.167 multiplied by 14p gives you 2.33, okay, pence to run, or 2.34, okay, if you round it up to 2 decimal places. Oven, 3,000 watts, turn it into kilowatts, divide by 1,000 gives you 3 kilowatts, okay. On for 2 hours, this is one that's really, really easy. 3 times 2 gives you 6, so 6 times 14. 6 times 14, let me just do that now. I can't work that out in my head, which is 84p. So our oven cost all that money, okay. And our bulb, it was on at 40 watts. Turn it into kilowatts. So we do 40 divided by 1,000 to turn it into kilowatts, which gives us 0.04, okay. How am I going to do that? 0.0, this is terrible, 4, okay, and then we multiply that by 3.5 to get the number of kilowatts. So we do 0.04 multiplied by 3.5, which gives you 0.14, okay. Light bulb is cheap, and times that by 14 pence per unit. So 0.14 times 14 gives you 1.96p. Okay, cheap, cheap, cheap. Cheap as chips. Chips aren't really that cheap. Okay, so bulb is left on for an hour, has a power of 0.1. This is easy, guys. You can do this yourselves. Yeah, 0.1 times an hour, which is 0.1 kilowatt hours times 14p. That's how much it costs. This one is on 15 minutes. How do we turn 15 minutes into an hour? That is right. We divide it by 60, which gives you 0.25. So 1.5 kilowatts times 0.25 gives you the number of kilowatt hours. 14p per kilowatt hour. By the way, in the exam question, it will tell you how much it costs per unit. I just used 14p because I saw it in one of the worksheets one time. Okay, so that was how electricity works and how to calculate the kilowatt hours. So what you also have is in a power station makes electricity, but when it makes electricity, it has a power of 20,000 volts. Okay, so what we do is before they go in the power line, we use a step-up transformer. Now, a step-up transformer steps up the voltage from 20,000 to 400,000 volts when it goes through the power lines. Because if we keep the voltage as high as possible, it means that less heat is produced when you pass it through. Because if you turn up the current, the number of amps, you're going to lose a lot of heat. But if you turn up the voltage instead, you produce less heat. So that's why they do it. That's why they put the voltage high. So the power lines lose less heat. Okay, but we don't want the factories and everything and the homes to be getting 400,000 volts because that will blow all their appliances. So we use a step-down transformer that lowers the voltage to a more usable 33,000 volts for the factories. But then you have another step-down transformer for the homes, which puts it down to the voltage that we use in the house, which is at 230 volts, which is a lot better than the really, really high voltage of 400,000. Okay, let's move on to the next one. Okay, so the order, what does it go in order in? Guys, pause it and have a go yourself. Which order are we going to put these in? What goes first? I'll give you a clue. First one is going to be the power station. Okay, and the rest of it you can figure out for yourselves. Power station, step up, national grid, step down, homes, factories, and businesses. Okay. Radioactivity. I think, shall I end it there? No, I think I'm going to carry on going. I don't think I've been going long enough. Okay, so radioactivity. What is a radioactive element? That is a symbol for radioactivity right there. But a radioactive element is an element that is unstable. So to become stable, it fires out radiation. Okay, and it might fire it out in the form of a particle, or it might fire it out as just as bursts of energy. Okay, like this. All right. Now, what you need to know is that the radioactivity can be very dangerous. This is your DNA, or any DNA. And what happens is as radiation fires out, it can damage the DNA, causing changes in the genes. And those changes in the genes are called mutations. Now, those mutations can actually cause cancer. Okay, so radiation can damage the cell, as we can see, radiation. And it can cause something called ionization. And that means it changes the structure of an atom. So this DNA is actually made up of atoms. And if the radiation fires towards it, it can change it. And that is called ionization. And if that happens inside the DNA, it can cause an error in the DNA. And an error in the DNA is called mutations. And mutation is in a change in the gene, which can lead to cancer. Okay, so this is a mutation in this particular gene, and it could lead to cancer. Now, the mutation could affect how the cell divides when it grows. Now, a lump of cells that grow out of control is called a mutation. Okay, well, it's actually, that's wrong. I should scrap that. It's actually a lump of cells that grow out of control is called a tumour. It's a silly mistake from me right there. And that is a tumour. See, these cells, they're all nice, neat lines, and they're grown under controlled fashion. But these cells have had an error in their DNA, and they've started dividing, and they can't control it. And that is what a tumour is, a lump of cells growing out of control. Yeah, that's what a cancerous tumour is, and that's what a tumorous cancer looks like right there. Okay, and a tumour from the skin right there. Yeah, so it's a lump of unorganised cells growing out of control, again caused by ionization of atoms, which causes a mutation, and a mutation is a change in a gene. And if that happens to a cell, it can controlling how well it divides, causing a tumour, which is a lump of cells. Now, when an atom is unstable, it will give out nuclear radiation. Now, can give out 3 kinds of nuclear radiation. It can give out alpha radiation, okay, which is a big heavy particle of helium, or it can give out a beta radiation, which is a little bit lighter, okay, it's a very small particle, or it can give out bursts of energy called gamma radiation. Now, as you remember from the electromagnetic spectrum, gamma radiation comes right at the end, doesn't it? Because it actually produces a lot of energy, okay? So what you need to know is you need to know how far alpha, beta, and gamma can actually travel. Now, this is the symbol for alpha radiation, and it's stopped by paper. This is the symbol for beta radiation, and it can go through the paper, and it's stopped by aluminium. This is the symbol for gamma radiation, and it can travel through paper, it can travel through aluminium, but it's stopped mostly by a thick bit of lead. Okay, so very dangerous. So, nuclear power stations. Actually, you have a very high chance of cancer if you live near a nuclear power station. German scientists have recently calculated that if you live near a nuclear power station and you've got children under 5, they are twice as likely to get something called leukemia, which is cancer of the blood, which is pretty scary, really. These are all the nuclear power stations in the UK at the moment. Okay, now some of these orange ones are the ones that have shut down. Sorry, the grey ones are the ones that shut down. And those are the ones that are being built at the moment, the ones in orange. And the yellow ones are the ones that are going to be built between now and the year 2025. Okay, so we are going more nuclear. And this one is going to be built between 2025 and 2040. So we are actually having more and more nuclear power stations because we're trying to reduce the amount of carbon dioxide and sulfur dioxide we produce. This is a nuclear power station. It looks slightly different to the normal power stations with the big massive 2 cooling towers. Okay, and if you actually look at it, like I've already said to you, that the nuclear power stations are actually very, very similar to normal power stations, but instead of burning coal to turn the water into steam, you use these little reaction vessels and these little control rods. These are the nuclear radiation bits. They heat up the water, or this, well, they don't actually heat up the water, they heat up this coolant liquid, okay, and then the water, these pipes go into the water, they're not actually connected to the water, and that water turns into steam. Steam turns the turbine, which turns a generator, which goes into the national grid and powers up all the big cities over there. Yeah, and the water is obviously recycled and goes back in, and you can see that loop of a system. Feel free to pause it and have another look at it. Okay, so this is what the nuclear power stations look like inside. Okay, I've actually got a YouTube video embedded in this, but we're not going to watch that because that'll be weird watching a YouTube for a YouTube. So I'm just going to skip past that. But that nuclear radiation is actually really, really dangerous, and it stays radioactive for a very, very long time. So what we do is we dig out these massive caves, and we put all of these barrels of nuclear radiation in it. And can you see these little layers over there? What do you reckon they're made out of? Yeah, that's right, they're made out of lead, because they need to stop the gamma radiation going through. So when this is full, it will be sealed off, and it will be left there. So that's how we get rid of nuclear waste. We build massive tunnels, and we get rid of it right there. This isn't as radioactive as the other one, and so sometimes they're built close to the surface. I'm not entirely happy with this one because the nuclear rods, barrels are very, very close to the surface. Okay, so fuel for power stations is uranium. Yeah, the waste produced is plutonium, or can be plutonium. It's not always like this, but this plutonium can be radioactive for thousands of years. Okay, there's another video. Let's skip that one. Okay, if you work in a nuclear power station, you have to wear this, which is a radioactive badge. Now, if radiation hits it, it will develop this photographic film. Now, if this goes white, then that worker knows he's had too much radiation for one day, and he's going to be sent home straight away. Okay, but they're also used as indicators of a radioactive leak as well. If the radiation is leaking and everyone's badges are being developed, then you know something's amiss, and then they'll sound the alarms and try and do something with it. So, You have to know how to handle radioactive waste, radioactive materials. So, because radioactive, like I said, can damage your DNA, can't it? So, when you're handling radioactivity, you have to know the precautions you have to take. You have to wear protective clothing, like a lead-lined apron. So you get an apron that's got lead in it to stop the radiation. You've got to keep as far away from it as practically possible. So that means holding it with tongs, not holding it with your fingers. So that's two so far. Protective clothing, like a lead-lined apron. Holding it as far away from you with tongs. Keep your exposure time. So if you get the radioactive source out, you've got to quickly do what you need to do and put it away. And you've got to work, and when you put them into boxes, they've got to be lined with lead, and they've got to be labelled. Because if they're not labelled, you could be handling anything, and someone could be handling radioactive material without really knowing it. Okay, now, you need to know of uses of radioactivity. Now, first one is alpha radiation. Now, alpha radiation can be used in smoke alarms. Okay, so how it works is that the alpha radiation actually ionizes the air, which means it knocks and damages the atoms. And then if the atoms are being knocked through and they're changing, that means the current electricity is going to flow. Okay, but if the smoke gets in the way, it stops the alpha radiation doing what it was doing, and the alarm will go off because the current will stop. You don't actually have to know how the smoke alarm works. You just have to know that alpha radiation is used in a smoke alarm. Now, if you ever open a smoke alarm to change the batteries, you will see this round little disc there, and that is what the radioactive source actually is a source of alpha radiation. Okay, so smoke alarms use alpha. In a normal setting, the alpha radiation ionizes the air, allowing electricity to complete a circuit. Smoke blocks the alpha radiation, so no electricity is produced, and the alarm sounds off. Like I said, you don't really need to know that. What you do need to know is that alpha radiation, one use of it, is use in smoke alarms. Now, we've been through alpha, now we've got to go through beta. What is the use of beta radiation? Now, beta radiation is used to check the thickness of paper or thin sheets of metal. Okay, now, the paper that you're working on right now is always going to be the same thickness. So what they do is they get the paper and they put it through these rollers, okay? And then what you're going to do is have a source of beta radiation, and you're going to have a detector here. Now, as the beta radiation is going to be firing across and the sheet stays a certain thickness, the same level of beta radiation is going to be detected because the same level is being blocked, isn't it? Okay? Now, if this sheet gets too thin, that means more beta radiation is going to get through, and the detector on the other side of it is going to pick it up, and the alarm's going to go off. And then the workers are going to come here, and they're going to adjust the rollers, or the machine can do it automatically for them. Okay, so you need to know about that, guys, because this was a 6-mark question not very long ago. And it had a graph showing all the beta radiation, and suddenly the beta radiation went high, I think it was, and which meant that the paper got too thin and you had to write about it. And I always stress to you guys, if they're giving you data, use it, write about it in the 6-mark question. Okay, beta radiation is used to monitor the thickness of materials such as paper, plastic and aluminium. The thicker the material, the more radiation is absorbed, and the less radiation reaches the detector. It then sends a signal to the equipment, because you can read it. Yeah, but I've just explained it to you. Now, use of gamma radiation. Now, ironically, gamma radiation causes cancer, but gamma radiation can also be used to actually destroy the cells of the cancerous cells. And that's what's happening right here. This person must have a brain tumor, and so the source of gamma radiation is being fired towards the cells, and because it can be very precise, they will actually just try and kill the cancerous cells. But it will kill the healthy cells as well, unfortunately. But, you know, we will need to kill the cancerous cells, and this is another example of this. And so the gamma radiation has been fired out maybe towards the tumor to kill all of the the cancerous cells. But unfortunately, like I said, some of the healthy cells will be killed as well. And this is another picture, gamma rays. Yeah, that is the target right there. Yeah, inside the head, and that's what's been fired out. Okay, another use of gamma radiation. Believe it or not, most of the fruit that you buy has been blasted with gamma radiation to kill all the microorganisms on the surface, like mold, and it makes the strawberries last a lot longer. That is called a radiation. okay, and it makes your fruit last longer. Also, when someone is cutting you up, well, let's hope that never happens, but if someone is going through surgery, you want to make sure that the knives of the surgeons are clean, and you can do that by blasting it with radiation to kill any microorganisms, because you lose a barrier, don't you? The skin is no longer there to stop the microorganisms getting in because you cut open. And so the gamma radiation kills all the microbes that do that. Okay, so they're used to treat cancer, but they're also used as tracers. Now, radioactive tracers are ones that can emit beta radiation or gamma radiation, and they can be used in hospitals to find out what's happening inside the body. So this person has swallowed some radiation, and someone on the outside is detecting where that radiation is going. So if you ever have to have this done, they will give you like a cup, and you will drink it, and it's a radiation, and when you drink it, they will have a detector on the outside detect where the radiation is, but it has a very short, something called half-life, which means that it doesn't stay radioactive for long. Something with a very long half-life will stay radioactive for a very long time. Something with a small half-life will only stay radioactive for a little while. Okay, now tracers are also used, as well as the body, they're actually also used to find leaks in underground pipes. Okay, so you put the radioactive liquid through a pipe, and suddenly have a detector on the outside that the person walks along, and when they get a big blast of radiation to the detector, they know that there's a leak. So instead of drilling everywhere to find a leak in a pipe, you put radiation down it. As soon as you see where it's coming out, you can put a signal over here, and that's where the workers are going to drill. Yeah. So tracers are not only used in the body, so gamma root tracers are also used in underground pipes. So you may be asking the question, why is it always gamma? Well, will alpha get through it? No, that's stopped by paper. Well, can beta be used? No, beta is stopped by a thin sheet of aluminium. So that's why we use gamma, because gamma goes through paper, goes through aluminium, stopped by lead, and it will go through this pipe, and it will go through, it will go through the leak in the pipe. Yeah, it won't actually make it through this thick one over here. Okay, so types of radiation, just as a summary, there's alpha, beta, and gamma. That's what they're stopped by: alpha by hand, beta by paper, and it was stopped by a thin sheet of lead, thick sheet of lead. Causes radiation, causes ionization, which means it knocks the electrons off, and it can become damaged. Alpha radiation, beta radiation. There we go. There are all the uses of it, and I will make a part 2 video to go through the rest of it. Okay, and next up we'll be exploring our solar system.